Let's face it, we are absolutely drowning in data. I mean, from medical research to the stock market, we've got more information at our fingertips than ever before. But here's the catch. More data doesn't automatically mean more clarity. A lot of the time, it's just more noise. So how in the world do we find that crucial signal that's hiding inside all of that complexity? Well, just take a look at this. This is what happens when a computer sifts through thousands of handwritten numbers. Now, each one of these little digits is its own complex data point with hundreds of different features. And yet, somehow, out of all that mess, the algorithm finds these stunningly clear clusters. It actually learns to see the difference between a 1 and a 7, or a 9 and a 4. It finds order in the chaos.
And that really brings us to the big question for today's explainer. How, right? How does a machine do that? How does it take this massive, totally overwhelming data set and find the simple, beautiful structure that's buried inside?
To get to that answer, we first have to wrap our heads around the core problem, and it has this fantastic, kind of dramatic name, the curse of dimensionality. It sounds really complicated, I know, but the idea is actually pretty simple. In any data set, every single characteristic you measure, that's a feature, or what data scientists call a dimension. So if you're looking at flowers, petal length is one dimension, petal width is another. The sepal length, that's a third. You get the idea.
And this slide right here shows you that curse in action. On the left, with just 2 dimensions, it's super easy to see 3 distinct groups of flowers. The pattern is just obvious. But look at the right. We add just 1 more dimension and the whole picture gets a lot cloudier. The groups start to mush together and that beautiful, clean separation just starts to vanish. And this isn't some visual trick. It's a deep, fundamental truth about data. As the source material puts it so well, our human intuition just completely breaks down in high dimensions. It's a paradox, right? Adding more features can actually make it harder for an algorithm to find the pattern, not easier. So we need some clever strategies to simplify things.
So how do we fight back against this curse? Well, our first technique is one of the most elegant tools in all of data science. It's called Principal Component Analysis, or PCA. And really, the best way to think about it is that PCA is all about finding a better, more useful way to look at your data.
So instead of just picking a few of the original features and, throwing the rest in the trash, PCA does something much smarter. It combines them. It basically rotates the entire data set around, almost like you're turning a camera, to find a brand new perspective, a new set of axes that capture the most important information, the most spread in the data, using fewer dimensions.
The whole process is actually pretty straightforward. It just boils down to 3 main steps. First, you center the data. Second, you rotate it to find the maximum variance. And third, you project it onto a new, lower dimension. Let's just quickly walk through each one.
Okay, step 1, centering. Just imagine all of your data points floating in space, forming a kind of cloud. The very first thing PCA does is find the exact center of that cloud and just moves the whole thing so that its center is at 0. This is really just getting everything lined up for the main event.
And now for the magic. Step 2, rotation. The algorithm takes that centered data cloud and starts rotating it, searching for that one single angle, that one perfect axis that shows the most spread, the most variation. A good way to picture it is like finding the longest possible line you could draw through an oval. That new axis, the one packed with the most information, that's our first principal component.
And the final step is projection. Once we've found that perfect, information-rich line, we just drop every single data point straight down onto it. It's like shining a light and looking at the shadows. And just like that, we've squashed a messy 2D cloud into a clean, single 1D line, all while holding on to as much of the original variation as possible.
And here it is. This is the payoff. Remember our messy flower data from before? This is what it looks like after PCA. Those groups that were overlapping, they're now beautifully separated along our new axes, PC1 and PC2. We didn't lose the important information. We just found a much better way to look at it. Okay, but what if you don't want to create these new kind of abstract features? What if what you really need to know is which of your original measurements are the most important ones? Well, for that, we have to turn to a completely different strategy, a technique called lasso. PCA and LSO really represent 2 totally different philosophies. You could say PCA is a transformer. It creates brand new features that are clever combinations of the old ones. LSO, on the other hand, is a selector. It looks at all the features you started with and does this amazing automatic feature selection, keeping only the most useful ones and completely getting rid of the rest.
So how does Lasso actually choose? The secret is surprisingly geometric. I mean, look at this slide. Lasso works by putting a constraint on the possible answers, forcing the best solution to be somewhere inside that blue diamond shape. Now, a similar method called ridge regression uses a circle, and that one tiny change, a diamond instead of a circle, makes all the difference in the world.
And here's why. Think of those red ovals as your model, searching for the best possible answer. The model expands outwards until it finally hits the boundary of the constraint. Now, with a smooth circle, it could touch literally anywhere. But because the diamond has these sharp corners that lie right on the axes, it's super likely that the model will find its best answer right on one of those corners. And when it does, the value for the other feature becomes precisely 0. It gets eliminated from the model just like that.
And you don't have to take my word for it. Here's the proof right in front of you. On the left, you can see Lasso doing its thing. As you increase the penalty, the lines that represent how important a feature is get forced all the way down until they hit 0. Poof, they're gone. Now compare that to ridge on the right. The lines get really close to 0, but they never quite touch it. Lasso selects, ridge only shrinks.
Okay, so let's just pull all of this together. We've looked at two really powerful but also very different ways of finding that precious signal hidden in all the noise.
So here's the simple breakdown. PCA transforms your data, finding a new and more efficient way to see it by creating these powerful new composite features. Lasso, on the other hand, simplifies your model by selecting a small group of your original, easy-to-interpret features. They're two different tools, but they're for the same common goal: taming complexity. And when you get right down to it, what these methods really show us is a critical lesson that goes way beyond just data science. In an age that's totally defined by information overload, maybe the most valuable skill isn't just being able to collect more data, but having the tools and the wisdom to distill it.
Which kind of leaves us with a final thought to chew on. As we face bigger and more complex challenges in the world, maybe the most important question isn't what else can we add to the pile, but what are we wise enough to ignore?